Boa noite a todos. Declaro aberta a 26ª sessão ordinária relativa ao 188º ano acadêmico. Os votos. Vê os votos. Queria novamente voltar ao assunto da visita da Academia Nacional de Medicina, Academia Nacional de Medicina da França. Lembrar que foi um evento extremamente importante. Pela primeira vez na história desses eventos, a Academia de Medicina da França abriu o espaço dentro da sessão ordinária, de tal maneira que nós tivemos um evento no dia de sessão. Tinham 90 acadêmicos franceses e 12 acadêmicos brasileiros. O presidente da Academia Francesa foi extremamente gentil e me deu a presidência da sessão junto com ele. Foi uma sessão de 4 horas, onde o acadêmico Fernando Vaz fez uma apresentação, o acadêmico Jorge Alberto Costa Silva fez uma apresentação excepcional e 2 apresentações da França. E eu quero também registrar em ata, que já foi registrado por mim na reunião de diretoria de hoje, um voto de louvor ao acadêmico Jorge Alberto Costa Silva, que eu não sei se ele está presente. Jorge Alberto, muito obrigado. O acadêmico Jorge Alberto Costa Silva se empenhou de corpo e alma, como tudo que ele faz pela nossa academia, e organizou uma sessão memorável, recebeu todos os acadêmicos na casa dele, no primeiro dia. No segundo dia organizou um jantar, onde todos os acadêmicos confraternizaram, e no dia da secção, após a sessão científica, ofereceu um jantar patrocinado para 40 acadêmicos franceses e mais tantos brasileiros, de tal maneira que eram 60, 80 pessoas no restaurante Brasserie 1900 Montparnasse, que é um Art Nouveau original. Então, acadêmico Costa Silva, meus sinceros agradecimentos pelo seu esforço. Lembrar que o custo para a Academia Nacional de Medicina foi zero, completamente zero. E isso graças ao esforço de todos os acadêmicos, que foram por conta própria, e o nosso acadêmico Costa Silva, que foi um tremendo anfitrião em Paris. Muito obrigado por tudo, além da sua palestra excepcional. Se tiver alguma comunicação dos acadêmicos, dá a palavra à plenária. Nenhuma comunicação dos acadêmicos. Convido, então, nosso acadêmico Silvano Martírio Raia para apresentar o professor Joseph Tector, da Universidade do Alabama, Estados Unidos, que vai nos falar de modo excepcional hoje. Nós abrimos esse espaço porque o professor Joseph Tector está no Brasil para um congresso e se dispôs a vir um dia antes para apresentar essa palestra para nós. Vai falar sobre Xenotransplantation, State of the Art. Por favor, acadêmico Silvano Raia.
É com muita satisfação que hoje eu apresento à academia o professor Joseph Tector. Ele é um dos expoentes da procura de órgãos adicionais para transplante. Os acadêmicos sabem que o número de candidatos a transplante aumenta continuamente, mas não aumentam os órgãos disponíveis. O aumento dos candidatos se deve, em parte, pelos bons resultados dos transplantes, e, em parte, porque a geração atual envelhece mais e oferece tempo às patologias a atingirem estádios que só podem ser resolvidos com a substituição. A falta de doadores pode ser exemplificada com a nossa casuística. O ano passado, em 2016, nós transplantamos no Brasil apenas 9% dos 34.542 inscritos. E essa diferença, essa desproporção, se faz ainda mais nítida em relação às crianças. Então, a solução mais atraente é aquela de usar órgãos animais, no caso suínos, que são os mais próximos a nós do ponto de vista de biologia, para os nossos enxertos. O professor Joseph Tector é o expoente dessa pesquisa que vai nos falar agora e, portanto, é com muito prazer que nós o recebemos aqui. Professor Tector, Joseph Tector, it's with great pleasure that we here in the Academy receive you, and we hope that in the early future you will finish and surpass the steps that still separate you from your goal of xenotransplantation. You are welcome.
Thank you very much. I'd like to thank the Academy and particularly Dr. Raya for the invitation. We're very excited to be here. The slides are not. So I'm going to start just to give a couple quick disclosures. Parts of this project that were particularly related to the sequencing of the genetics of this pig were funded by United Therapeutics, and I have formed Xenobridge Limited Liability Company and applied for patents related to pig engineering and xenotransplantation. So why xenotransplantation? I think that answer is actually very, very simple, and I'm not going to spend a lot of time on it. I'm going to use some data from the United States, where if you look at the wait list for kidney transplantation, say what? Closer to the microphone? Okay. So if you look at the wait list for in the United States, there are more than 98,000, actually there's just over 100,000 people that are waiting for kidney transplants. And each year we do less than 16,000. So many, many patients never ever get a transplant. So when you talk about xenotransplantation, and before you start doing a lot of work in it, you have to answer one fundamental question, and that is, if everything is set up in a good situation, will pig kidneys work in a human being? And the answer to that is not entirely simple. There's a number of problems with xenotransplantation as a solution to the donor organ shortage. The first problem is that human beings, you and I, we have antibodies that cross-react with sugars on the surface of pig cells and cause immediate graft rejection. And so those antibodies are a barrier to transplantation. But genetic engineering in pigs has been developed and cloning so that now you have the opportunity to genetically modify the pig and eliminate some of the antigens to which those antibodies bind to. But that's been problematic because we have been unable to find embryonic stem cells in pigs. In mice, it's been very easy to find, and you can engineer embryonic stem cells in a mouse in a dish for months and still make all 3 germ layers, or for our purposes, make a baby. In pigs, we haven't found those, so we have to use cells from the body, and those last only about 3 to 4 weeks before they lose their ability to make a baby. And then the tools for genome editing up until 2011 have been very primitive, so that we're only able to make very simple modifications. In addition, if you're going to use pigs as a source, you need to prove or show that these pigs do not harbor pig viruses that are common pathogens in human beings. We'll talk about that, about 29 that we've identified. And then you need to have assays to test for these zoonotic viruses. So people have laid the groundwork. Xenotransplantation is not a new concept. They have laid the groundwork for what needs to be done. And so in 1989, they had a meeting celebrating the 25th anniversary of Keith Reemsman's chimpanzee kidney transplants, one of which, he did 6, one of which lasted 9 months in a patient who was a school teacher who went back to work, and she ended up dying from electrolyte abnormalities, not rejection. But Dr. Kalm, who's one of the really fathers of modern organ transplantation, said if you were going to talk about putting a pig organ into a human being, the first step would be to take the pig and make it so that the rejection went from being a violent, very strongly antibody-mediated one to a less antibody-mediated one. Then Dr. Starzl in 1994 wrote, based on his experience with allotransplantation and his experimental experience with xenotransplantation, he came up with the notion that xenotransplantation, that rejection in a xenograft, is mechanistically the same as the rejection for an allograft. And what you're seeing in a xenograft currently is antibody-mediated rejection. And once you were able to dial that barrier down, that we have the drugs with chemical immunosuppression that would make this feasible. And so that really stuck with our program. And so we've really held on to that notion that when you transplant an organ into a human being, the human immune system has only so many ways that it's going to deal with it. And so if you look, a glycan, the first barrier to transplantation in the early 1960s was antibody mediated. And that's because, number one, we didn't realize that you had ABO antibodies and we couldn't transplant across ABO blood barriers. Then if you look at what came next is people that were sensitized, okay, so women that were multiparous or had multiple babies, people that had blood transfusions, or people that had a previous failed renal allograft. They had antibodies. So those antibodies would cause hyperacute rejection. And as you drop down on the antibody level, you started to get what you'd call from hyperacute rejection to antibody-mediated rejection and transplant glomerulopathy later. Then, if you look at a xenograft, you've got these glycan antigens. I'm going to show you some data that shows you that the HLA antibodies that human beings make, some of them cross-react with the pigs. And so it turns out we have a great opportunity with a pig to engineer out the interaction of those antibodies by deleting antigens. So the first step was developing a preclinical model for renal xenotransplantation. And so we took pig kidneys and put them into rhesus monkeys. And so one of the sugars that is responsible for about 70 to 85% of the antibodies that you and I have to pigs is the alpha-gal sugar. Now, this pig kidney also had a human decay accelerating factor gene in its genome, but we can't prove that there's any expression on the cell surface. So for purposes of academic honesty, I'm telling you that it had an HDAF gene, but for all intensive purposes, this was just a gal knockout. And so we did cross-matching like you do for a clinical transplant with flow cytometry. They had a lot of IgM, a lot of IgG, the graft thrombosed with a lot of parenchymal hemorrhage, C4D staining in the glomerulus, and it's classical antibody-mediated rejection. So if you get a little bit better cross-match, and so this is a situation where the IgM was still high, but the IgG cross-match was actually quite good. That would be negative. And then you use T-cell, classical chemical immunosuppression with T-cell depletion, so kind of like rabbit anti-thymocycline, but we use anti-CD4 and CD8 antibodies. Then we use belatacept, which is a co-stimulatory blockade, and steroids. This graft rejected at 14 days. And if you look at it, this is a medium-sized artery, and these are lymphocytes on the endothelium, and you can see the lymphocytes are lifting off the endothelial layer right here. That's endotheliolitis. That's pathognomonic for cellular-mediated rejection. And if you show that to a pathologist, they're going to tell you that that's cellular-mediated rejection, and they're not going to distinguish that it was a xenograft. Now, if you use a little bit stronger immunosuppression, so we gave an anti-CD40 antibody, which is a stronger co-stimulatory blockade molecule. This shows a biopsy at 108 days. It's clean, without evidence of basement membrane thickening in the glomerulus and no thrombotic microangiopathy. So now, with our preclinical model, we can tell you that our mechanisms of rejection are B-cell mediated with preformed antibodies or de novo or brand new antibody production, and then there's T-cell mediated rejection. And so we focus with the genetic engineering component specifically on the antibody-mediated portion and specifically on the preformed antibodies. So our hypothesis is that prolonged kidney xenograft survival is feasible if the level of antibodies, xenoreactive antibodies, is low enough to avoid early humoral rejection. And so we put these gal knockout transplanted kidneys into rhesus monkeys screened specifically for low levels of xenoreactive antibodies. And so the exact immunosuppressive regimen isn't that important, okay? But I'm going to tell you that we gave a CD4 and CD8 antibody to T-cell deplete. It's just like rabbit anti-thymocycline that we use clinically. And then we used this anti-CD154 antibody, and we can't use that clinically. And we'll talk about that a little bit later. And we use cell-septin steroids. Now, the important thing for you is, depending on what the cross-match was. So you see sorry, I'm messing that up. If you see, this is the cross-match, okay? So this is IgG, that's IgM. The red bar is an animal with a high amount of antibody, and that went out at 5 or 6 days. The blue and the white are lower levels of IgG. There's some IgM, and you can see that those animals had a good creatinine out to 160 and 310 days. Now, when a kidney starts being rejected, it spills protein in its urine. It's certainly by antibody-mediated mechanisms. And you can see here, the protein spilling was very late in the course, at about 11 months for this 310-day survival. So that's very, very good evidence that the graft is working quite nicely. Now, it's important that these grafts both failed. So why did they fail? Well, it turns out they had antibody-mediated rejection. And so if you look at a biopsy of a kidney transplant, there's thickening of the glomerular basement membrane. You can see that duplication right there, the thick wall on an electron microscopy. This onion skinning is pathognomonic for thrombotic microangiopathy, which is, again, another hallmark of antibody-mediated rejection. And then looking at confocal microscopy, at the 310 and the 160-day survival, you have IgG, you have IgM, and C4d, a complement activation in the glomerulus. So these things are going down from antibody-mediated rejection. Now, just to give you a rough idea, this is, and I don't really want to focus on the fact that this is the immunosuppressive regimen. We changed them a little bit. Here's your take-home message. This had a bad cross-match, this 18-day survivor. That's explainable. This had the next worst cross-match. But then we went out, this one went 310. This animal ended up going out 585 days. It says 405 here, but this slide's a little bit old. This animal had to be put down because it got into a fight with another animal, but had a normal creatinine at 70 days, and the biopsy was normal. And then this animal went out over 500 days, and this animal went out over 500 days. And the take-home message from that is, and this is just to show you that the creatinine stays normal or acceptable till late in the course after transplant. And so our take-home message is that xenoantibody binding to xenoantigens remains the proximal barrier to xenograft survival, and that identifying these antigens and deleting them in donor pigs should continue to be the focus of xenotransplant research. In addition, we feel like our clinical data suggests that once histocompatibility testing suggests that humoral or antibody-mediated rejection is not an immediate barrier to transplant, it's going to be reasonable to test this in some patients. So let's talk about the known xenoantigens that pigs have that we, humans, have antibodies to. So the first one that was described is the alpha-gal antigen, and that's an antigen that is made by an alpha-1,3 galactosyl-transferase, and that's a gene that we have deleted during the course of evolution because it's thought to have conferred protective immunologic survival advantage at one point. And so David Cooper is the first person that really identified this as a xenoantigen in around 1994, and so that's one antigen we need to target. The next one that we needed to target, and we did, is N-glycolyl neuraminic acid. So there are two ways that mammals handle sialic acids. The first way is with N-acetyl neuraminic acid, and then there's N-glycolyl neuraminic acid, where they put this hydroxyl group on. That's the only difference. and it's produced by an enzyme, cytidine monophosphate N-acetyl neurominic hydroxylase. We deleted this during the course of evolution, and there's very good evidence to suggest that we deleted it because it conveyed protective immunity to a prevailing strain of malaria that was going around many, many years ago. But because we've deleted this gene and we don't hydroxylate N-acetyl neurominic acid, when we see N-glycosyl neurominic acid on bacteria, we make antibodies to it. So that's another target. Then the third target is an antigen that we really don't have a great handle on what it is. It's called the SDA antigen, and it's made by an enzyme called beta-1,4 N-acetyl galactosaminotransferase. That really doesn't mean much, but when you add this gene to a human cell, humans start to have antibodies to it. And the way it was found by Chris McGregor and Jerry Byrne is they screened baboon serum from animals that had rejected gal knockout hearts. And so this just shows, this is a kidney, a wild-type kidney that has the DBA binding indicating the SDA lectin is present in the vessel, in the medulla, and the glomerulus, and here's a knockout animal where it's absent. That's all that tells you. So we have 3 genes producing xenoantigens, the alpha-1,3 galactosyl transferase, the SEMA gene, the hydroxylase making the N-glycosyl neurominic acid, and the beta-4 gal NT2 transferase. So we talked about genetic engineering in pigs and the limitations. So now we need to talk a little bit about what those barriers were and what's happened. So again, embryonic stem cells have been unable to be located in a pig, and it's largely because the blastocyst stage in a pig is from day 7 to 17, and they have a very funny shape, so they can't reproducibly find them. So this allows us to use somatic cells only and make simple or quick modifications. And we used homologous recombination, which is the proverbial looking for a needle in a haystack. And so the problem is it would take us up to 3 years to make a single knockout of one gene. So you make a pig, you look for your cell, and you'd find one copy of the 2 copies knocked out. Then you'd make a pig, and you'd get babies from that had one gene knocked out, one copy knocked out. Then you'd have to wait 6 months for females, 10 months for males to reach sexual maturity and breed them. And then you'd have to do it again, so that it was 36 months by the time you had a pig with both copies of one gene knocked out. That's just too slow. So fortunately, nuclease-based genome editing came along in about 2011 for zinc finger nucleases, 2012 for TALENs, and then 2013 for the CRISPR-Cas9. And so I'm going to talk about the CRISPR-Cas9 because it's easier, more flexible. And so the CRISPR-Cas9 is a primitive immune system for bacteria. That's how they handle viral attacks. And it uses 2 RNAs. It uses a CRISPR RNA and it uses a tracer RNA so the CRISPR RNA binds to a viral sequence. The tracer RNA binds to the end of the 3' end of the tracer sequence, and that tethers the Cas9 nuclease. And then the Cas9 nuclease eats both copies. It just grinds it up like a wood chipper. And so then the virus is gone. That's how it deals with it. Well, Emmanuel Charpentier and Jennifer Doudna realized, hey, if we put a little linker loop of RNA, we could create a single guide RNA, and we could target any part of the genome that we wanted in a programmed fashion. So the single guide RNA that you use is typically 17 to 20 base pairs in length. And so anybody that's involved with PCR, when you order a primer, this is no different. You order these single guide RNAs. And so what you need is 2 guanine residues at the end of your guide RNA, and there's a site in pigs roughly 1 in every 500 base pairs, and you can target both strands easily. And just to tell you why it's easier than zinc finger nucleases or TALENs, the zinc finger nucleases and TALENs, they are tethered, the nucleases are tethered to the DNA binding element. And so you have to if you want to knock out more than one gene, you'd have to design a different set of TALENs or different set of zinc finger nucleases. Whereas for the Cas9 system, you order as many different guide RNAs as you want, and they'll bind to the site, and the Cas9 nuclease moves freely, and you can knock out, you can multiplex, which means knock out more than one gene at a time very easily. So now I'm going to tell you how we use this CRISPR-Cas9 to make our new pigs. And so what we do is we figure out what genes we want to knock out, we order the guide RNAs, we electroporate the Cas9 nuclease and the guide RNAs into the cell, and then since the cell's GAL is expressed on all cells, and since we want to knock out GAL in every pig we make, because it's a xenoantigen, we can run these cells through an IB4 lectin column. And this IB4 lectin column hangs on to any cell that has GAL. So if the cell makes it through here, it's like 99% GAL negative. And the great news is that enriches for your cells so that about 50% of the cells that make it through this column have all the genes knocked out that you want. That's just how it works out mathematically. So then you do nuclear transfer like you do for a mouse, and you put the nuclei in a nucleated oocyte, put about 100 of them into a female that's been ready to be impregnated, and then at a month you have a decision to make. You can terminate the pregnancy, clone, genotype and karyotype your cells, your fetuses, and pick a fetus that has exactly what you want, and then reclone it, and then you get a whole litter of a single type, or you can let it go to term. We've made 4 different kinds of homozygous knockout pigs in a single pregnancy, so which is great for when you want to test things and have really solid and detailed controls. The other great thing about it is from the day you say, I want to make this pig, to the day they're on the ground is between 135 and 150 days. So that's a huge difference if you can knock out multiple genes in less than 150 days as opposed to one gene in 3 years. So we told you about the three genes we wanted to knock out. So we created triple xenoantigen knockout pigs. So we made guide RNAs to the galactosyltransferase gene, the SEMA, the hydroxylase gene, and the beta-4-gal-NT2 transferase. And we put them with these wild type. These are liver-derived cells. We've made them with fetal fibroblasts. It doesn't really matter. We run them through the lectin column. That gives us our gal knockouts. And then we flow cell sort for the new 5GC or the hydroxylase knockout and the beta-4-gal. And then we do nuclear transfer and come up with piglets. And so these pigs, the SEMA-gal, the gal, SEMA, beta-4-gal knockout pigs, they grow. Actually, we have some now that are 500 pounds. There's no phenotypic abnormalities noted. This just shows you, so this is going to show you the phenotype and the genotype. So if you do flow cytometry looking for the expression of gal, the wild type has a lot of gal, which is this IB4 lectin. The knockout has none. If you look for the new 5GC, it's in the wild type, it's missing in the knockout, and the DBA lectin or the SDA antigen is missing in the knockout, it's present in the wild type. This is just the Sanger DNA sequencing showing you the 2 copies of the gal gene, what was knocked out, the 2 copies of the SEMA, and you'll notice there's 3 of the beta-4-gal. There's a duplication of that gene, that's why there's 3. That's great, we knocked out all 3 genes, but what does it mean to somebody? So before you get a transplant, one of the last things that happens is they cross-match your blood with either, they've moved in clinical transplant to HLA beads, but in the past, for about 40 years, they used PBMCs from the donor, and they'd make sure you had a negative cross-match. So this is one person getting cross-match against the wild type, the gal knockout, the SEMA gal, and the triple knockout. So you can see with the wild type, they have a lot of IgG binding, a lot of IgM binding. You look at the gal knockout, it's improved, but it's still quite positive. You look at the SEMA gal, it's improving. Now with the triple, this person has a negative cross-match, meaning that we are unable to detect antibody against this pig in this person's serum. If that were an allograft, you'd go ahead and transplant him. Now this just shows you cross-matching for about 30 people, maybe a little bit more, but each one of these dots is a person, and they're in each one of these cross-matches. So this is IgG binding, this is IgM binding. This box is under 5,000, which is where you want the IgG and IgM binding. And you can see in the wild type, nobody's close to this box. The gal knockout, they're getting closer, but nobody's in it. The double knockout's still closer, and with the triple, you can see that a lot of people are starting to get in there. And we've cross-matched over 1,500 people, and 30% of the people that we've tested, waitlisted patients, have a dead negative cross-match to this pig. 70% have a negative IgG cross-match. So we are starting to move toward a situation where we could transplant somebody without expecting early antibody-mediated rejection. Now, the old standard cross-match before we did flow cytometry was a cytotoxicity assay where you'd incubate the serum with the cells, and you'd add complement, and then you'd measure for cell death. So we did that. And what we got was we looked at people that had no HLA antibodies, unsensitized. And you can see that for IgG, a lot of them are negative. For IgM, it still comes out to be about 30. It's less in this population, but as we've done more, it gets bigger. But the highly sensitized people that have antibodies to about 80% of donors, they end up having a positive cross-match. Not all the time, but a lot, and most of the time. So we're going to have to work on that. And so now we're at a situation where we've got a genome-edited pig kidney going into a monkey. We're testing more xenoantigen deletion, okay? And then we're going to try and minimize preformed antibodies. We'll do xenoantigen elimination with our gene editing, test it with histocompatibility testing, and then use chemical immunosuppression. So this is a gal and a beta-4 gal. So monkeys have SEMA, or they make new 5GC. So we can't test that antigen knockout in a monkey. So we can only test the two antigens. So we did that. And so we did 2 transplants. And one of them, the cross-match looked negative, but we didn't do a CDC, the old school cross-match. And it turns out our reagents to measure antibody binding in a rhesus aren't as good in a human. So one of them went out at 5 days from antibody-mediated rejection. And that had a positive cross-match. So when this went out, we went back and tested it. And it turns out that rhesus still have a lot of IgM, or a fair amount of IgM, to this double knockout pig. But the other animal went out 468 days with a creatinine that was under 1.5 for most of its course. And this shows you the biopsy at around 270 days, and you can see that's a much healthier glomerulus where there's not thickening in the basement membrane. There's no spill of protein in the urine until very, very late in the course. And so CRISPR-Cas is able to be used to eliminate xenoantigens in donor pigs to create a negative cross-match to a lot of patients on the wait list. And we already have a sizable portion of people that we could try this in. As far as preclinical data, it's becoming increasingly promising for a proof of concept clinical trial in patients with a negative cross-match. However, the people that are highly sensitized, which is unfortunate because they're an ideal candidate to transplant because they don't get a chance a lot, those people, a lot of them, are going to have to wait for more genome editing of the swine leukocyte antigen. And I'm not going to talk about that today, but we've got a lot of data and information on that, and we've made a lot of progress. So prerequisites to a clinical trial, we think we're going to need proof of principle preclinical data using tacrolimus as our immunosuppressant instead of CD154, because that's what we use clinically in transplant. We're also going to have to be able to produce pigs with a favorable cross-match, which we've done. So our next steps, we've created these beta-4 gal knockout pigs. We're going to start, they were born recently, we're going to start doing transplants in the rhesus monkeys in late June, and we're going to substitute the CD154 antibody that we cannot use clinically for tacrolimus, and we're going to transplant them into a series of about 6 to 10 animals using T-cell depletion, tacrolimus, mycophenolic acid, and steroids. That's a clinical immunosuppressive regimen. We also have to develop assays to test donor pigs for zoonotic pathogens and develop a facility to produce clinical grade pigs as kidney donors. And so I'll tell you that we have identified 29 viral pathogens that the FDA is certainly going to be interested in. Mark Pritchard at our institution has developed and validated nucleic acid testing, and we are able to pick up as few as 4 copies of a virus in a milliliter of a clinical specimen. So we feel like that is largely on its way. And this just shows you that with a quantitative PCR, if there's no virus, we're able to go out 40 cycles and pick up nothing. but we're able to pick up, it's later, you got to run a lot of cycles, but as few as 1 to 5 copies we're able to pick up. So we think we're in good shape there. We have a clinical grade pig facility that is a shower in, shower out. It's going to be, we're going to have the animals are going to be born by C-section, so they're going to be cesarean derived, they're going to be deprived of colostrum so they don't get anything from mom. We have the ability, if any of the animals ever get sick, to flush a room with chlorine dioxane so that we don't have to flush the whole facility. This is going to house 30 pigs at a time. It's just a little think tank kind of incubator for us to get our clinical trial off the ground. We have our FDA application, a draft of it completed. We think we're debating whether we can hand it in without the data with the FK506 or the tacrolimus treated rhesus monkeys or not, but our question, the trial is very simple, and that is, will cross-match negative recipients of pig triple knockout kidneys transplants receiving allograft immunosuppression and allograft viral prophylaxis achieve 1-year dialysis-free survival? And currently, there's 2 patient populations we're thinking about. People over 65 who in our center at the University of Alabama, we have 3,000 people on our wait list. They have at least a 5, more likely an 8-year wait, and they're not going to do well on dialysis to receive a kidney. We're also have identified people with anti-HLA-B antibodies in particular. So if you have an HLA-BW4, BW6 antibody, those antibodies don't cross-react with our pigs, so we're going to evaluate some highly sensitized people. We have a draft of the IRB application that we'll submit later this year. And again, so here's the trial. We're going to take a triple knockout pig. We're going to use, which we've done with xenoantigen elimination through genome editing. We're using histocompatibility testing, identifying appropriate donor-recipient pairs. That's a paradigm that we've used in clinical transplantation since the mid-1960s, and then we're going to use T and B cell clinically approved immunosuppression to try and achieve 1-year dialysis-free survival. And that's where we are today. So with that, I'm going to thank the Academy, and I'll take any questions.
Thank you very much, Dr. Tector, for this amazing presentation. Algum acadêmico quer fazer um comentário da plenária? Marcelo Morales.
Congratulations for the important work and the opportunity to share the data with us. Thank you.
Thank you.
My question is regarding if you found any renal dysfunction abnormality in the knockout animals.
You mean in the pigs?
In the pigs.
No, the pigs have entirely normal renal function. It's a good question. The thing that when you worry about knockout animals, did we change something? And this is what I'll tell you. The genes that we've knocked out, alpha-gal, you and I have knocked out. Old world monkeys have knocked them out. The SEMA gene, you and I have knocked it out. The beta-4 gal-NT2 transferase, we have knocked out the lectin or the glycan that gene makes. So these are genes that we function normally with. So that always gives me some comfort that it's not going to be as big a problem as we had initially thought.
And so how long did you follow this renal function in those pigs?
So we have pigs that are about, I want to say, between 15 and 18 months old. So we have followed them to that point. As you know, very few pigs are given the opportunity to live 10 or 20 years. So some of that we're going to learn in evolution. But so far, the kidneys seem entirely normal.
Thank you.
Obrigado. Acadêmico Ricardo Cruz. Quem?
Thank you for a nice presentation. Thank you for coming. What is your opinion about facial transplantation? The face is not an organ. What is your opinion about this?
So facial transplantation, I'm not involved in it. What I can tell you is when you see the people that they're trying to help, it's incredible that those people are suffering unbelievably. So I applaud their bravery in trying to go forward with that. The one thing I would say is going to be really important for them moving forward is if you look at how transplantation has been successful, it has to have people that get involved in it and take care of those patients from A to Z. So you can't separate doing an unbelievable operation, face transplant, and then have somebody else, take care of them entirely. I think it's going to be really important for the development of that field that the people that are in it stay in it from beginning to end. And I think, to me, I'm not sure if that's happening or not, but I hope that it is. So I think it's wonderful for the people that are so disfigured and suffering. So I'm rooting for them to be successful.
Thank you, Dr. Tector. Mais algum comentário? Marlupe.
Thank you, Professor. It was a very nice presentation. I'd like to ask you about xenotransplantation is also related with possible transmission of endogenous retroviruses. So my question is about what's the point? We already know about many endogenous retroviruses in pigs, and monkeys are primates. What's the risk for humans when we think about this endogenous retroviruses crossing the barrier between different species?
Yeah, I'm glad you brought that up. It's an important consideration. And so in the late 1990s, early 2000s, people were very concerned about the risk of viral transmission. And one of the things that's happened in the last 15 years is people have really started to study and understand how new viruses and pandemics form. And so using a lot of that new information, they've been able to go back and evaluate the risk. And I'll give you an example. If you look at HIV was people were able to go back to morgues in various cities in the United States and find HIV virus in specimens from people before 1920. And so they looked at it from the standpoint of when does it occur, when does it show up in the population in mass. But what people have started to realize is our exposure to pigs through skin grafts, believe it or not, in the 20s and 30s, they did a lot of testicle transplants to try and rejuvenate men. And those did not transmit a virus. So people are starting to feel like the risk is much lower. The other thing is porcine endogenous retrovirus. Number one, if it is a problem, it's very susceptible to new antiretroviral drugs. So people are comfortable that it is going to be very manageable. In addition, to get a PERV virus in a human cell, the only way it's ever happened is if they take very, very strong effort to make a specific, there's PERV A, B, and C. There's about 62 copies of PERV in each pig cell. But PERV A and C have to recombine in a specific way for it to get in a human cell. Now, our pigs are PERV C negative. They don't have PERV C. So if they're raised in a colony, they're cloned and raised in a facility where they never encounter another pig, that risk should be really, really minuscule. But I don't think it's something that can be discounted. The bigger thing that the FDA is worried about now is garden variety pig viruses that can cause disease in humans. I hope that answers your question.
Thank you, Dr. Tector. Dr. Acadêmico Daniel Tabaque.
Thank you very much for your interesting presentation. I've been involved with stem cell transplantation for several years, and I was wondering, I read some early reports that on xenotransplantation there was a lot of coagulopathy and thrombocytopenia, and I wonder in your model if this has been described in the knockout mouse pig, if this has been described. And the second question is, considering all this degree of immunosuppression, T-cell depletion, and all these immunosuppressive drugs, the appearance of secondary tumors and leukemias have been described as that a concern? Thank you.
Sure. So as far as the thrombocytopenia goes, it has been seen, but the thing is, if you look at a human-to-human transplant, if you have antibody, you get a coagulopathy. So you get the same kind of thrombotic microangiopathy. As you get rid of antibody, that coagulopathy goes away. And it turns out, I'm not going to talk about it, but it was a big problem for the liver because they became thrombocytopenic. But as you get rid of the antigens, that thrombocytopenia goes away. So that is a humoral or antibody-mediated rejection problem. As far as, what was your second question about the neoplasia? So we're going to use clinically what's currently used as far as immunosuppression. So we're not going to use super levels of immunosuppression. We're going to go to clinic with allograft levels. They will have an increased risk for those kind of issues, just like anybody who gets an allograft. We have not seen it in the monkeys yet. That doesn't mean it won't happen. The other thing is, though, is as we start to get feedback on these people, we can continue to genetically engineer. I haven't talked about it, but we're able to swap genes. So we're able to cut out genes that are offensive to the human immune system and replace them with human counterparts. And so I think over time we'll be able to continually down-regulate the immune system's initial interaction and hopefully minimize or decrease the immunosuppressive burden these patients are going to face.
Thank you, Dr. Tector. Acadêmico Silvano Raia com a palavra.
Thank you for your massive data presentation. And before ending, I would like to ask Professor José Medina, who has the greater experience among us in renal transplantation, that will comment briefly what he thinks about this new way.
Yeah, thank you, Professor. Many years ago, when we first started looking at xenotransplantation, the phrase that we heard was, xenotransplantation is the future of transplant, and it will always be. Maybe we have an answer in this model that you presented. Thank you.
Gostaria de perguntar se o nosso querido correspondente estrangeiro, que está aqui na bancada acadêmica com todos os direitos, Dr. Rodrigo Viana, gostaria de fazer um comentário. Por favor, Rodrigo.
So thank you. Actually, I got a chance to we worked together for 10 years, Dr. Tector and I, in Indianapolis, and I saw how all this research started. And I had the same view probably 10, 15 years ago that xenotransplantation was always in the future. But if you think about the 60s, people that did, all the hepatologists, nephrologists, everybody that also thought that transplantation would always be in the future, and it happened. So I think the fact that in Tector's lab they were able to shorten this period from 3 or 4 years to 100 days. So yeah, it's not in the future anymore, because what was considered 20 to 30 years now is down to 2 to 3 years. So I think he has answered the question to the future. The future is not 20 years, the future is very soon. So I do think that this will happen.
Muito obrigado, Rodrigo. Mais ninguém quer comentar? So, Dr. Tector, thank you very much for coming to the National Academy of Medicine and present this amazing lecture. Thanks a lot.